Good afternoon, students. Today we will discuss the topic microwave activation. It is an important concept of green chemistry. And let us see the introduction about microwave activation. Microwave induced reaction enhancement, that is more chemistry, has emerged as an important non-conventional method of reaction activation. It involves a short response time and better yield of products. These are the two main advantages of microwave heating. Microwave irradiation induces specific interactions between materials and waves of electromagnetic radiation subjected to dielectric heating. In this, microwave oven is considered as the reactor. Microwaves range from 1 centimeter to 1 meter in wavelength in the electromagnetic spectrum. They are located between infrared and radio radar frequencies. Major part of the microwaves is assigned to radar technology and telecommunications. A frequency of 2450 megahertz, that is equal to 12.2 centimeters under vacuum, is fixed by law by domestic or industrial purposes. According to Planck's law, E is equal to h nu by C. The quantic energy involved is 0.3 kilocalories per mole. This energy is too low to induce any excitation of molecules or to provoke any reaction. Microwave energy is non-ionizing. The main material wave interactions are of electromagnetic nature by penetration. They do not alter the molecular structure of the reactants or reagents. It provides only thermal heating by penetrating into materials very significant, close to a few centimeters as for the wavelength. Now coming to the theory of microwave heating. This microwave heating results in rotational changes in the molecule. For example, polar molecules display the property that they can be oriented along an electric field. This mechanism is called as dipolar polarization. In the absence of dipoles, in the absence of this field, dipoles are oriented at random and molecules are subjected to Brownian movement. In the presence of continuous electric current, all the dipoles are lined up together in the same direction. If submitted to an alternating current, the electric field is inversed at each alternance. The dipoles, they tend to move in the direction of the field. Such a characteristic induces stirring and friction of molecules, which dissipates as internal homogeneous heating when compared to classical heating. Solvents with higher dielectric are preferred because of higher heat transfer. Now let us see the pictorial representation of the theory of microwave heating. For example, as we have already seen, the frequency of radiation involved is 2450 megahertz, that comes around 12.2 centimeters. Now, if the molecules are without any constraint, when there is no radiation applied, they are involved or they are aligned at random. Now, when it comes to the dipolar polarization, orientation of dipoles in an electric field, we can see that all of them are aligned in a single direction. Then when you submit it to a continuous electric current, that is alternative field of high frequency, there will be inversion of orientation at every alternance. You can see this. This is normally when you apply the current, and in the case of alternative electric current, there will be inversion of orientation at every alternance, and this results in stirring and friction of the molecule, as we can see in the picture. And because of the stirring and friction, there will be internal homogeneous heating. So this is a diagram of the influence of electric field on a dielectric compound. This diagram explains the theory of microwave heating. Next, acceleration of organic reactions by microwaves. Material wave interactions. We can see the thermal effects and also the non-thermal effects. In the thermal effects, there are two mechanisms, dipolar polarization and charge space polarization. Dipolar polarization is regarding the liquids, whereas charge space polarization is regarding the solids. And what is the interest here? You can see better homogeneity in temperature, and it is specific for polar molecules. The microwave effects increase in polarity. Now, when it comes to the non-thermal effects, there will be variations in activation parameters. Example, K is equal to A exponential delta G by RT, and you can see the small variations. Dipolar polarization, previous organization of polar systems, entropic effects, favored orientation, hot spots, high localized microscopic temperatures, enhancement in collision properties. Now let us look at the advantages of microwave heating. The heating involves high speed, no inertia. Heat affects the products only. It is easy to use, quick energy transfer in the whole mass without any superficial overheating. Heating takes place in the core of materials with subsequent homogeneous temperature. The profile of gradients in temperature are inverted when going from classical heating to microwave heating. Selective heating in polar molecules. Very fast heating. Rise of temperature is 10 degrees per second. This system is especially efficient in the case of poor heating conductors. Now, let us see the advantages of microwave heating in the form of a picture. The materials are heated following an original procedure. In the case of classical heating, you can see that the heating is only superficial, that is around the periphery. In the case of microwave, we can see the radiation penetrates into the walls of the container. Then in the case of selective heating of polar molecules, the mechanism of heating is called as dipolar polarization. In the case of solids, it is called as charge space polarization. In the case of dipolar polarization, if you take a 50 ml liquid of DMF, apply 600 watts of electricity and 1 minute, you will get the temperature of 140 degrees. Similarly, if you apply the same conditions to water, the temperature will be 80 degrees centigrade. And with CCl4, it will be 25 degrees centigrade. In the case of charge space polarization, if you take 5 gram of solid, apply 850 watts in 6 minutes, Fe3O4, MnO2 and CuO, all of them will acquire a temperature of 1200 degrees centigrade, whereas Cu2O will acquire a temperature of 89 degrees. So you can see in the graph, temperature, that is with, in case of classical heating, there is gradual rise of temperature, whereas in microwave heating, there is a sudden rise of temperature and it will remain constant at a certain point. In the case of microwave, the increase rate in temperature is 10 degrees centigrade per second. The system is especially efficient in the case of poor heating conductors. Then specific effects of microwaves. Purely non-thermal. We have already seen this. The thermal effects involve dipolar polarization, charge space polarization. Result is better homogeneity in temperature, specificity for polar molecules. Microwave effects increase with polarity. Then we have taken one Lewis experiment. In this experiment, we can see the temperature gradient in the case of microwave and also in the case of classical heating. We can observe that there is reduction in apparent activation energy and non-uniform temperature on a molecular scale. Now, let us see the benefits of organic synthesis under microwave. Very rapid reactions, and the products contain high degree of purity, better yields are obtained, homogeneous heating, low operation cost, and environmental heat loss is avoided. At the same time, let us also see the limitations of microwave. Boiling points of solvents are reached rapidly. This leads to safety problems, absence and measurement and control of temperature. Limitations can be overcome by using solvent-free techniques. To operate with a monomode reaction with permanent control of temperature. Then there are two types of equipments. Two types of reactors can be used in the laboratory. Multimode systems. There are domestic ovens with limited power and are characterized by non-homogeneous distribution of electric field due to several reflections of the waves on the metallic walls of the oven. Monomode reactors, homogeneous distribution of electric field and can be used with a low emitted power with a high energetic yield. Reaction vessel may be Teflon, Pyrex, borosilicate, polystyrene containers are used. These materials are transparent to microwaves. They absorb radiation poorly and can withstand temperature generated in the reaction mixture. Then sealed reaction vessel. If reactions are to be carried out under pressure, then sealed systems are employed. Example, Teflon bomb in sealed vessels. Very high temperature and pressures are rapidly attained. Risk of explosion increases during microwave irradiation. Open vessel reactions carried out by using simple, inexpensive, safe equipment. Example, open Borosil beaker, conical flask or Erlenmeyer flask. Simple one is a tall beaker with a loose cover having much larger capacity than the volume of the reaction. So this is about the theory of microwave. And these days, much of the research has been carried out by using microwave in organic synthesis.